Yeah, my name is Vladimir Temlyakov. I'm originally from Russia, but now I'm working and affiliated with University of South Carolina from the United States. I'm also affiliated with two places in Russia. One is Steklov Institute for Mathematics, and another one is Moscow State University, Lomonosov Moscow State University. So, and my main topic is approximation theory, well, basically one of the topics of this semester.
My name is Hansen. I am here at the University of Cambridge, where I run the Applied Functional Harmonic Analysis group. And my specialty is computational mathematics, covering foundations of computations and harmonic analysis, approximation theory, numerical analysis, inverse problems, and a lot of different areas that are involved with computations.
One of the main topics of this program is approximation theory. It is very interesting to witness what I did during my 40 years of research, that this topic, approximation theory, from being comparatively theoretical topic like 40 years ago, has developed into a very, very involved topic for applications, and it is included in a lot of applications in engineering and other stuff. So one of the main challenges for this our program was to establish even more connections between theoretical stuff like approximation theory and real applications. And for that, we invited many people from different subjects like compressed sensing and learning theory and other areas. And I think we have succeeded this in a pretty good way.
So another part of the program is data science. Data science is enormous. And what is very interesting these days are the connections between new approaches in learning, particularly deep learning, and also approximation theory. So one important thing that we are facing these days is that deep learning and artificial intelligence might take over many problem-solving tasks that humans have, but we also have the issue for which these data science techniques and AI techniques take over traditional algorithms in the sciences. And to understand the fundamental issues of these cases, we need to dig into the foundations part here, and that means understanding the mathematics behind this. And there's a lot of very interesting connections between approximation theory, compressed sensing, and new developments in data science and AI and deep learning. And these things have been essentially the focus of the theme of the program.
As to this nowadays, we can see the change from problems which were very popular, for instance, 100 years ago, 80 years ago, and most of those problems were one-dimensional. Now, the new topic is multi-dimensional, not just 2-3 dimensions. Sometimes the quantity of interest depends on thousands of dimensions. Now, for instance, in banks, when they give credit for like 30 years, they need to recalculate every month. That means 30 years is 360 months. So they need to have this in 360 dimensions. And this is a huge challenge. And there are many, many problems which, like technique, which work pretty well in univariate case and dimension 2, does not work for these huge dimensions. So that was one of the challenges which we encountered with. And I think now people understand much better what are the challenges and how to go around those challenges.
So as for the impact in general, I would like to point out 2 examples. So compressed sensing, which is a part of the theme of the program, has received substantial attention over the last years, and as of 2017, compressed sensing has been FDA approved for use in MRI and is now used all over in all the big MRI production machines, and is now standard in the hospitals. Another case which is of great interest is that also FDA has approved deep learning techniques for automated diagnosis as of April 2018. So these are the typical showcases for which we can show that actually the mathematics lead to something.
The main challenges, I would say, this is the way from pure theoretical stuff to the stuff which could be understood not only by theoreticians but also by people who can really apply this stuff into practical decisions. And this is actually a big challenge because usually it requires not just one or two layers between pure theoreticians and pure practitioners, I would say, but it requires several layers. And how to go through all those layers is a big challenge. And on the other hand, here in this semester, we invited people from different groups and how to communicate between different groups. Sometimes even notations, even language is kind of different. So this is one of the challenges too. But this is the whole point of the semester, to get people together and to try to overcome all these challenges. And I think we are doing pretty well. And the workshops, which are concentration on this, help a lot in that.
Another problem in modern data science is that a lot of the engineering that's been done, that's been incredibly successful, is essentially ahead of the mathematics. And the mathematicians here have a great job in essentially tidying things up and to understand what is going on. This is not the first time in the history of science where mathematicians need to essentially provide the foundations later after the experiments are done. This happens typically in physics a lot. But what has happened over the last years is that it has been engineering techniques that have been incredibly successful, but the understanding of that is not really there. And that's where really the mathematical understanding has to be, or is completely crucial, and we're not there yet. And hopefully this program is going to foster a lot of research that we're going to do in the future to be able to capture all these delicate issues.
So one of the potential applications, but this is a very obvious application, everybody encounters with the results already, this is images. Because what is image? Mathematically, we can think about the image as a function which depends on two variables. But certainly when we do this computationally, we need to digitize and we consider an image as consistent of pixels and other stuff. And now the big question is, could we compress this image such that keep only, like for instance, 4 or 5% of that information and do not deteriorate dramatically the quality of this picture? This is important in many cases because very often we do not have enough memory to keep those images, or we have the limits for the channels to transmit this. For instance, if you communicate with a satellite, but can we do this or not? And it turns out that in many cases we do have an ability to compress these images dramatically. And this is one of the points where this purely mathematical ideas and techniques help a lot. So this is one of the very challenging and very successful application of pure mathematics.
So another issue with imaging is what we call inverse problems. Typically, if one goes to a hospital and gets a CT scan or an MRI scan, the machine does not actually produce an image directly, but measures something different that has to be decoded back into an image. That process of doing the scanning is time-consuming, and it's uncomfortable for the patient, and it's expensive because of the time it takes. There's a whole crew that has to take part in this. And so we would like to reduce the actual scanning time by using the fact that images are compressible, as we say, that they can actually be represented much more efficiently. One can also use that to shorten the time that's used in medical imaging when the scanning is done. How to do that most efficiently is a very delicate mathematical problem. There are, methods that are well established, but there's also now new data-driven techniques that are based on learning that are emerging. And these techniques have potential, but we don't know exactly how good they are and what the potential is.